This video is on VSEPR and an introduction to molecular geometry. Okay, so your note paper has a statement at the top, which I did not write, and it says, while Lewis structures are useful in determining the number and types of bonds between atoms, they do not tell us anything about the three-dimensional structure. So we're going to start this discussion with methane, or CH4. So if we draw CH4's Lewis structure, it's a pretty simple one, and it looks, of course, like this. Okay, and that's its structure. Okay, and if you had to make a decision based on this picture as to whether or not this molecule is planar, which means flat, okay, all lies in one plane, it surely looks like it is. Okay, so it appears to be planar. And it also appears like the angle here is 90 degrees. Okay, so it appears to be planar or flat and has 90-degree angles, what we call bond angles. Okay, and in fact, it is not. So the key word here was that it appears to be, and it is actually neither one of these things. So it isn't. Okay, and that's because the problem that we have now encountered is that we are drawing 3D molecules are being represented on a 2D surface, as in this, piece of paper, or in this case, my iPad. And so that brings in a lot of error into this discussion because we're talking about molecules that are 3 dimensions and we're only representing them on a 2-dimensional surface. So it's going to be problematic. So see, what really happens is, we're so used to the XY coordinate plane, okay, but really what we now have to consider is that we have not only the X and the Y, but we have the Z, okay, axis, which all of a sudden brings us into 3 dimensions. And so that changes everything. So, because I can't show you a model in this video right now, I'm not going to attempt to explain CH4's shape yet, and we'll get to that later, okay? But it's just what we need to understand right now is that shapes are misleading on paper because we're only in 2 dimensions. So then how do we know what the real shape of CH4 is? And it's something that's called the VSEPR model. Some people pronounce that as VSEPR. They make it a word, okay? But it's an acronym, and it stands for valence, shell, electron, pair, repulsion. Okay, and it's just the first letter, VSEPR, and that's how they name it. If I had to pick one word in this 5-word name that's the basis for VSEPR, it's the word repulsion. Okay, and so ultimately, what does VSEPR say? Well, it says something we already know, which is that electron groups repel one another and want to be far apart. Okay, and that makes sense because we know electrons are negative, and negatives have never liked each other. They've always repelled, and so they repel one another, and they want to be as far apart as possible, which is going to lead us to they are going to strive for largest bond angle possible. So that means in my example of methane, okay, up here, where we had a bond angle of supposedly 90, if I can get those electrons in those bonds farther apart than 90, then that's a good thing because they don't like each other. And so that's what happens, is that contrary maybe to what you believe, we actually can get those electron groups further than 90 degrees apart, and it's because we have to consider the 3rd dimension. And so I can try to draw it for you real quick. What really happens is we have the carbon in the middle, and then I have a hydrogen here and a hydrogen kind of here, okay, which notice this angle, I know it's drawn kind of funny, but it's bigger than 90. And then I have, and this is hard to do on paper, but I have a hydrogen that's coming toward me, and it's drawn with this like little wedge. And then I have a hydrogen that's going away from me, and it's drawn with a dotted line. And the bond angles here actually end up being about 109 degrees. And so because 109 degrees is further apart than 90 degrees, this is the structure that it takes. Okay, it's actually not planar, and it doesn't have bond angles of 90, so it's very different. Okay, and this shape is actually called a tetrahedral. We'll get into all of that later. Okay, so what we have to talk about now is how do we go about thinking about the correct geometry for these molecules when we know that drawing the Lewis structure can be very misleading to us. So we're going to do an example, and we're going to walk through all of the kind of vocabulary that you need to know. So our example is with the ammonia molecule, which is NH3. So if I draw a Lewis structure, let's see, I should count appropriately here. I know I have 8 electrons, and this one's a pretty easy structure. Whoop, so single bond, single bond, single bond, and everybody's good. Okay, so that Lewis structure is fairly simple to draw. Now, while that's a correct Lewis structure, it's actually not a correct geometry, and that's what we have to understand. That we can draw Lewis structures that obey all the laws of Lewis structures, but yet they tell us nothing about the geometry. And so we have now discovered that Lewis structures can be pretty misleading. So we need to go through some vocabulary. Some of these things we've already talked about. So the first thing we need to talk about are what are bonding pairs of electrons. Okay, well, those are your shared electrons, or your looks like it says shaped. Oh my gosh, sorry. Shared electrons. Those are your electrons that are in the bonds. Okay, so we know this is a shared electron pair, this is a shared electron pair, and this is a shared electron pair. Okay. So then what are your non-bonding electrons? Well, those are your lone pairs, and those are assigned to one atom and one atom alone. And so in this case, it's the nitrogen who has the lone pair in this Lewis structure. Now, because my picture is getting kind of crazy, I'm going to erase those arrows real quick. You can leave them on your paper if you want to, have them marking that. So we already knew those things. The bonding electrons are your shared electrons, and the non-bonding pairs or the lone pairs are assigned to one atom. So what we don't know are what are these things called electron domains. And so electron domains are the bonding electron pairs plus the lone pairs on the central atom. Okay, so in this case, our central atom is nitrogen, and we're talking about how many bonding pairs of electrons do we have? Well, if we're talking about bonding pairs of electrons, this is a bonding pair, this is a bonding pair, and this is a bonding pair. Okay, so I have 3 bonding pairs of electrons, plus I have 1 lone pair on nitrogen, which is going to give me 4 electron domains. Okay, and that's how I count electron domains for your central atom. You count how many bonds and how many lone pairs are on your central atom. There's only one trick to that, and so I'll go ahead and label that. The trick is that a double or a triple bond counts as 1 electron domain. So like let me think of something real fast. Okay, like carbon dioxide. This is carbon dioxide's Lewis structure. And you might be inclined to say that carbon as the central atom has 4 electron domains, but it doesn't. It only has 2 because this double bond is counted itself as 1 domain, and then this double bond is counted as the second domain. So that's the only trick that you might want to keep in mind later as we're practicing. Okay, so then what does this tell us? So once we have established how many electron domains are on the central atom, we can then predict the electron domain geometry, which is basically the arrangement of the electron domains around the central atom. Okay, and this is going to stem from one of 5 types of geometries. And so this is the first kind of cheat sheet that did I not put it in here? Oh man, it's not in here. Okay, so, well, I can use it like this. Okay, so the 5 electron domain geometries, okay, are, and look, it even tells you, see, number of electron domains. So if I have 2 electron domains, then my electron domain geometry is something called linear, okay, which makes sense. If I have 3 electron domains, then my electron domain geometry is something referred to as trigonal planar. 4 electron domains is that tetrahedral that we've already mentioned with methane. Okay, and then I have to scroll up here. 5 electron domains is something called trigonal bipyramidal or trigonal bipyramid. And then 6 electron domains is something called an octahedral. Okay, so those are your electron domain geometry. So this chart's very helpful because it's labeled electron domain geometry, and it depends only on how many electron domains you've counted. So we just counted 4 electron domains. So we go down to our chart and we read that 4 electron domains is going to give me an electron domain geometry of tetrahedral. So for NH3, its electron domain geometry is tetrahedral. But there's one more thing we have to consider, which is something called the molecular geometry. And the molecular geometry is the arrangement of just the atoms around the central atom. Okay, now this gets tricky, and I'll have another video where I have models and can show you this stuff, because this has to be a very solid understanding of what molecular geometry stems from what electron domain geometry. Okay, so there will be an additional video that will help us with this. But for now, we have a chart. So what we do is we go down to our chart, okay, and we know that for NH3, we have 4 electron domains, and let me back this, so you can see the title. Okay, so we know we have 4 electron domains, and we know our electron domain geometry is tetrahedral. What we now have to think about is how many of those domains were bonding and how many were the non-bonding or the lone pairs. And so if we scroll up, we can remember that we had 3 bonding and 1 non-bonding. So here it is, 3 bonding and 1 non-bonding gives us a molecular geometry of something called trigonal pyramidal or trigonal pyramid. And notice NH3 is actually the example that they gave us. So what the molecular geometry does is it takes into account that, yes, there's something up here taking up space, which is a lone pair, but it's not an atom. And so the molecular geometry is just the shape of the atoms alone, but still taking into consideration that lone pairs take up space. So this is a tough discussion if it's the first time you've ever seen VSEPR. We're going to be working with the models a lot. Like I said, I'm going to have a second video that's going to show you the models and to walk through all of these electron domain and molecular geometries and talking about bond angles and whether they're planar and all of that. So that will be an additional video. But this was your intro to